Well, thanks very much, Alex. And it's a real pleasure to be able to speak in this symposium honouring Ken. Ken's been and continues to be a real scientific inspiration for me. I a lot of his papers, all of his papers, and actually he's been a real source of support and he's been a real source of support and a great mentor for me over a long period of time. It was really great to be able to honour him in this meeting. So as my title suggests, I'm actually going to talk about batteries, which is a bit of a new thing for me. About 4 or 5 years ago, my colleague Simon Clark and I were asked to join the Faraday Institute project, which is the Faraday Institute in the UK funding mechanism for basic electrical cars. And we were invited by Sweden Corp in the UK to join Future Cap, which is their funding project, and we were going to handle the new materials ideas and new cathode materials. So I'm going to talk about some of the work that we did in this area. So I guess batteries don't really need any introduction, everybody knows this, but the reason I have this slide here is so that we can see that the important bit is that energy storage happens with the metal. So initially cobalt, and then we add manganese and nickel to improve performance. But there's a problem with these metals, and that's they're just not very sustainable. There are issues to do with the mining of cobalt, human rights, and nickel and manganese are moderately expensive and quite rare. So if we look at this version of the periodic table, this periodic table shows us the economic availability of these metals. And if we think about our battery system, we're going to need a transition method. We're going to use the Redox chemistry of a transition method to store the energy. And if you look at your transition method, you're allowed anything that's green. And that really means you have titanium, iron, and rather it's not just rhenium. If your rhenium is supposed to be green, we're not going to reuse rhenium. So I chose titanium or iron, and basically Simon and I basically said, well, let's focus on making batteries. And we're going to divide up into the table. I'm going to do the oxides, Simon's going to do the stockpile. So what we're going to try and do is make lithium-ion batteries out of iron. And immediately the audience said, I think these already exist. That's like here are bad elements. These iron cathodes actually already exist, right? So lithium-ion phosphate, the thing you go out by a plant, there's a really good chance the battery is lithium-ion phosphate. But lithium-ion phosphate has problems. It has a relatively low potential and has a low volumetric density. So it's a bit of an issue. So I came into the review by knowing, well, can we think about making all oxide iron cathodes? And we're going to try and use the iron 3 plus iron 4 plus Redox cathode of a higher operating temperature. And really, starting from a naive chemical viewpoint, saying, well, we try this. How hard will it be? Is this going to be easier or is this something to do? And what you can do is, first of all, start with saying, well, let's just have a look at lithium-ion oxide. So the thermodynamically stable form of lithium-ion oxide is this disordered orbital structure. And you can say, well, let's just try and get some lithium out of it. And if you try doing that, nothing happens. Because this is a stone cold instrument. The electron transport in this thing doesn't work at all. You can't do electron transport. So you can make it anisotropy, and you can, so if you use static chemistry, make the particles really small, you can get some redox activity, but what you then find is you have another problem, because what you find is your lithium iron oxide transformed into this thing out here, LiF508. And if you do a quick bit of mental resonance, you can see this is an iron 3 material. This is an iron 3 material, so we haven't oxidized iron at all, you've oxidized it. So this shows our real problem that we had a change in structure and we have unstable iron form. And we can see a lot of this problem relates to the migration of iron from oxidable side to tetrahedral side. And just from a fundamental chemistry point of view, we can see that it's going to be actually quite easy because iron 3 plus is iron. So it doesn't have a strong negative field, so it won't be oxidable or tetrahedral. So it will move around as it's oxidates. That's one of our big issues. And it turns out you can take any of the various polymorphs of LiF and you try this trick. So you basically try the electrochemical cycle and all of them transform to this spin out. And you can cycle this spin out. And if you look in a paper and people claim that LiF has some story, it isn't. It's So this is our problem. Problem number one is how do we stop this structural change on electric cycle? The problem number two relates to the stability of iron force. There isn't really any sign of iron force in many of these lithium deficient iron oxide cathodes. And we can see why if we just look at the sort of more normal picture of lithium oxide. So this is a R3 band structure of lithium oxide, that is the oxygen band, here are the cobalt 3D bands. And as we take lithium out of the system, we're removing lithium, we're oxidizing the cobalt. So this 3D band comes down, but what isn't probably widely appreciated is by taking away the lithium states here, these are pushing the oxygen band down. So actually the oxygen band coming up with the cobalt band is coming down. And you get to a position now where the top of the valence band is actually the oxygen, not the cobalt. So in a LiClO2, we haven't used half of the capacity, because if we go any further, we start with this point. And the problem for iron is exactly this. How do we stabilize iron 4+, because we really don't see any sign of it. So this is problem number two. How do we stabilize iron 4+, or how do we stop the anion redox ruining the valence? Well, what we did was we took a view of looking at stabilizing the iron lithium ion oxide system by using the post-transition method. So things like antimony and tellurium. And what you find is if you introduce things like antimony and tellurium into the composition, they stabilize that sanguine stack framework. So here we have a layered material, not very layered, with each layer is of the same composition, but we have an ADA stack of oxide ions, here with the hexagonal structure, and then what we have is ordering of antimony and iron. Here's lithium. But as soon as we actually insert it into this system, to make an iron surplus compound, the iron jumps out of this site because now it's a lot bigger and it migrates to a different site. And we end up with this ordered structure. Now, so we're getting this iron migration problem. Now, in this material here, the issue is that we actually end up with a charge ordering between ions and ions grid. And that's so stable that we can't actually take the lithium ion. So this is quite good. But what we find is by substituting some of the iron iridium, we can break up this charge order framework and cycle the ion. In a related system, now we have tellurium, it's the same framework. Now we find we have a pretty reversible ion migration. But the problem with this material is that the tellurium redox coupling is really close to the iron 2, iron 3 couple. And we end up reducing tellurium and Symp for the element. So again, what we can do is we can replace some of the iron with indium. What that does is expand the iron with the oxyhedron by chemical pressure. And what you find then is that actually pushes the iron redox couple up, and you get away from the tellurium couple. And it's like what it do. But in these cases, what really things, this system is pretty hard. We can sort of mitigate against the cation migration, but we do it at the expense of the electric affinity. We also don't think you can stabilize high oxidation state of iron in materials where you take out lithium. So we make this state here, which is an iron 3+ state with a slightly different structure. And we can take out lithium chemically, and again, we get the iron migration from tetrahedral to an octahedral site. But this formally iron 4+ phase, this coordinates the iron 3 and iron 5, which then stops you putting the lithium out again. So this is the thing. So the initial things we looked at really weren't very encouraging. It's pretty hard to make cathode material out of iron because you have this problem with the migration, and you have the problem with the stability of iron. But what I really want to talk about for the rest of the talk today is some work we've just done recently that's gone public, looking at this polymorph of LiNO2 that's called TLiNO2. It has an ordered first side structure, but it's a rather metastable structure. It's further fortified with Bruce. What you can do is take a sodium form beta NaFeO2, which has an ordered versite structure. So hexagonal postbacking of the oxide layers, and then we fill half the tetrahedral site with iron and lithium in ordered stripes. And what you can do, what these show is you can replace the sodium with lithium to make what's called TLiNO2, which is the Na2 basically. So what we plan to do is then substitute some of the iron that have been more gathered as an attempt to try and stabilize this framework so we don't get the migration. and we don't get this redox. We do the cation exchange in a slightly different way, but we can't get it complete in repeated recipe. So we get about 90% exchange at this level, but we then treat the material with solid lithium bromide rather than super or suspension, and that gives us a good conversion. And what we can then do is make the equivalent substituted lithium phase. And so what I'm showing you here are the lattice parameters of the solid solutions. Here are the sodium phases that we will make time without the gallium, and here are the lithium phases. Once we've done this substituted. And you can see actually the idea of this slide is to show that these materials are dramatic. They work nicely. You'll notice that the aluminium 1.0 phase is missing. It's lithium aluminum phosphate. You want to start thinking of the same can't stabilize this. And what I'm really going to do is focus on this middle position here where we've got a 50% substitution of iron by aluminium gallium. So what we want to do first of all is check the structure is correct. And these are just X-ray data. We can't find the lithium with X-ray data. So what we can do is take neutron pair fraction data. So this is neutron pair fraction data from Polaris. This is one of the 5 data banks from the normal data here. This is just illustrative to show that, yeah, this material where we've got 50% substitution and part of iron by aluminium, it gives us a nice structure. And the reason I show this is if you then look at the gallium, it's very slightly different. You see there are a couple of extra little peaks, but within the gallium case, what we get is iron gallium ordering. So in the aluminium case, we have a random distribution of iron and aluminium on each of the brown sides. Within the gallium phase, we now get gallium iron ordering along these. So we get slightly different operations. So what we want to then do is think about the because we're interested in the structure, we're interested in the fundamentals of these materials rather than the recycling. What we're going to do is we're going to do the redox chemistry. We're not going to do it electrically because if you then have to recover the material from the electrical cell, it really compromises your structure. So here are our oxidizing and reducing agents. We're going to start off by looking at the reduction, and we're going to use butyl lithium as our reducer. So what we're going to do is take our oxide materials, stir them up in UV for a couple of days, and then filter them and see what happens. So what we find in the aluminium case, where we've replaced iron by aluminium, this is the dead loss. The aluminium really doesn't help the fingers. We get elemental iron forms in this side, C plus oxide, and just chaos. The whole thing just aluminium isn't helping. But in the gallium case, once we get more than 30% substitution, we actually retain this. And we can get a good crystalline material post-treatment with these oligos. So we can lithiate this material. And again, if we take a neutron diffraction data, we can get a nice fit to the data. But actually, this model doesn't contain any extra lithium. So we know chemically we've got the extra lithium in there. So finding the lithium is actually a bit of a challenge. Lithium is quite a weak scatter of neutrons, but it has one useful picture there. So it's a negative. So what we can do is calculate a Fourier difference map and look for the large negative things, which I'm going to see here, which we can then locate in the crystal structure and find that the largest negative piece sits in the empty of each site, which sit within the versatile frame. So you put these into a crystallographic model and refine that, and you find that the lithium stays in these sites, and we get a composition of Li 1.5 by gallium 2, which is both consistent with chemical analysis, also kind of consistent with common sense. So you see this would be an ion. And we can check that ion is being reduced by doing some absorption measurements. So this is Zane's data. So what I'm showing here in the red is the Zane's edge for the iron gallium material before we lithiated. We've got 2 standards here for us, 3. And post lithiation, we can see that this edge moves the lower energy consistent with reduction. And if we look at the bond lengths of the system, they get longer, consistent with our bond lengths. So it looks pretty good that we can reduce this system by lithium extraction. So what about oxidation? Well, what we're going to use for our oxidation chemistry is this nitronium ion. Yes, we're going to use nitronium BF4, in 6 nitrile as our oxidizing agent. And we're going to stir up our reagents. And now we see actually the aluminium is open. So once we get more than an 8th substitution of aluminium for iron, we can actually stabilize the vertical framework and retain material. And in the gallium case, we need 40% substitution to stop this canal forming, but again, we can get retention. So to check that we actually did this, we didn't just decompose our sample, we wanted to show, first of all, it's reversible. So we take these oxidized materials and treat them with lithium iodide. It takes quite a long time, it takes 2 or 3 days, but the lithium will go back into the system. We can see that happens around the chain. So that's a reversible reaction. And our chemical analysis shows that we are removing about 0.4 lithium sulfide. So we can then the neutron data, the sort of structures, and what we find is nothing remarkable. So the crystal structures are retained, we just have particle frequency on the lithium side, consistent again with our chemical analysis. And what we see, certainly in the iron aluminium case, is a slight decline in the average bond length around the iron, but in the gallium case, there's almost no change. And if we look at the Zane's data, we try to ask the question, have we actually got any iron core? So far, we haven't seen iron core in any of this. And so now I'm plotting the absorption edge of this iron aluminium material. Now I've got 2 different standards, one for iron 3, one for iron 4. And the green line is the oxidized material. You can see it's moved a little bit higher, but really not very much. And when you take it back, move back a little bit, but it's not clear you've got very much iron there. You should have oxidized at least half of your iron before. It doesn't look like that stuff. In the gallium case, it's the same sort of situation. The oxidation, it's a bit hard. We lose this feature here, but the oxidation really don't do very much. So it's really not clear we've got it. So the question is, do we have oxidized oxygen? Do we have anion oxygen? Because we know we've taken electrons out. What did we take? Well, we can look for oxidized oxygen by using soft X-ray absorption. So what we're going to do, although what Ken was talking about before, is we're going to use soft X-rays to excite electrons from the core 1s orbitals of our oxygen to any orbital band that has any oxygen stream. And basically, they're going to get, the electrons are going to get excited up into the hybridized iron 3D oxygen band, and then the hybridized iron 4s4p. And once we excite an electron from this core oxygen 1s orbital, what then happens is electrons in orbitals that have oxygen 2p character will then drop back down and into the photon. We'll catch those photons, and what we then do is plot out the total fluorescence here. So basically, plotting out the total number of photons as a function of excitation. And so what I'm plotting out here are the soft X-ray absorption spectra of the iron aluminium case, the fluorine after oxidation, and the same with gallium. And you look at those 2 spectra and say, well, they look pretty much identical. If you look really closely, you can see a bit of a threading in the oxidized case, but if I was trying to convince you that we've got oxidized oxygen in this species, but these are the data. But there is another thing we can do. And it turns out, if you look at this system, we can think, well, where did the oxygen hold, if you like, be? Well, the empty state is going to be at the top of the valence. That's where they're going to be. And it turns out, if you've got empty state here, you can get this extra, well, first of all, you're not going to see them, because what you need is then to see in the soft X-ray, you can excite an electron up into that empty state. And it turns out the overlap is really small. That's what we're going to see. But what you can find is an exciton between the empty state and the field oxygen. And so what that means is when electrons drop down out of these bands, we're going to see an emission from an electron that sits in this band, which actually releases less energy than we expect from an interaction with these elements. So if we could energy resolve the emitted radiation rather than this total calculating or measuring the total fluorescence here, if we could basically energy resolved emitted radiation, we should be able to see it. And so what you can do is bring resonant inelastic spectroscopy, and that's what I'm doing here. So now I'm showing you excitation energy destruction as we have it here. But now, rather than spectrofluorescence here, we've got the emission energy here, and that's contour color, so the number of photons. So we can take this data here and we can just integrate it. So I can integrate it to these columns of excitation energy and recreate my subject. But we can see that, from what I said before, this next one means that I'm expecting to see some low energy or lower energy emission from the oxygen to cool down. So I should see an enhancement in emission here after oxidation. And I hope, showing you this is the oxidized material, I hope you can see that there is something there. There's an extra emission or enhancement of emission in this specific area, which is consistent with oxidized. And we can reinforce that idea by doing, rather than a total integration, we can do a partial integration of this low energy region. So this is what the pristine material looks like, and this is what the oxidized material looks like. You can see this here would be consistent with the emission or from these oxidized oxygens. Now, the nature of those oxidized oxygen species is something we don't know what it is. We don't think it's a peroxide ion. We don't think it's a superoxide ion. It's a ligand cold. I tend to mean from the literature. That's what people call things they don't know what it is. But we know that we've oxidized oxygen. That's probably a little bit of iron, but we don't know the form of that. Okay, so to finish off with, what about the electric impulse? Well, what we want to do is ideally cycle ion 2, 3, and then 3, 4, or whatever this anion model is here. We're going to focus on the gallium system where the reducing material is also stable. And so if we do a charge-discharge series of cycles, so people are familiar with this format of the data, I'm plotting out the capacity, milliamp hours per gram. This is how much lithium we're taking out at the beginning. So the oxidation would go up, and then the reduction would go. And if you look at the data, you can see it looks a bit strange because it looks like we've got two types of features. You can see there are some features like here in the oxidation, which are really high, and then in the oxidation down here, you see there's a low percentage. It's like we've got two separate processes. As if we've got this iron 2, 3 redox couple, and then something that happens that, like I said, or we would think is how. So we can plot this data in a slightly different way. What we can do is plot out the same data, but now we'll run in total of how much lithium we've got on the plate. So we start here with our lithium 1.0, and the first thing we do is an oxidation here. So we take out about 0.05 lithium's unit. And what we can do is keep track of the ion oxidation state and what we think, or how many electrons we think we've oxidized at the oxygen. And we can say that in this first step, we don't actually oxidize any iron. It's all anion. So our ion oxidation state is 3, and we get about 0.05 electron worth of anion. In the discharge cycle, you can see it's vertical. We don't have any lithium in it, so we get below 3 volts. And we take this as basically being limited, but we're not reducing these oxidized oxygen. That's the reverse. What we're doing now is reducing iron 3 by 2, so that takes us a little bit. We then do another charge cycle, so we draw it in out. Then if we look at the shape of this curve, you can see that there's a low potential oxidation and then a high potential oxidation. And we make the distinction that this is iron redox, so this is oxidizing iron 2.3, and then this is anion redox. And we can partition the electrons to give us the ion oxidation state and the oxidation. And again, in the reduction, we come back down again, no indication of oxygen reduction. This is all iron. And so as we go through the cycles again and again and again, what we see is we oxidize more and more oxygen because that's irreversible. And we're suppressing this iron oxidation state further and further and further down. And so what we end up with is a situation where we can't put any more lithium in the system because we're already at ions. You'll notice from the diagram, actually, we have an ion oxidation state that's less than 2, but that's just a feature of us choosing this potential here to pick up iron cutoff, which between ion oxidation and anion oxidation. I'm sure there's a bit of crossover. But the take home message is what we're really doing is we're oxidizing oxygen irreversibly. And that pushes the ion oxidation further and further down. So we can't reinsert it. So effectively what we do is we start here with this iron 3 phosphate. Initially we can put in lithium to get an iron 2 phosphate, but on cycling, we end up oxidizing the oxygen. So we end up with an iron 2 phosphate, which is pretty good. And that really, after all this, that kills you with a cathode material, you basically can't do this. This irreversible oxygen redox means that this isn't a viable. One thing that is surprising is that we get anion redox competing with the iron 2, iron 3, not the iron 3, iron 4. That seems generally strange. So what's going on there? Well, we think this is a feature of the chemical pressure I mentioned before. Because if we take our stuff, let's put this the sodium, iron, gallium, where the iron and gallium are ordered, so we can look at the local coordination of iron and it's formed by the sun. That's exactly what we're going to study. But when we replace sodium with lithium, the much smaller lithium within the structure expands with the transition that comes like. So we basically make all the iron oxygen bonds longer, which lowers the bond over the sun. What it's really saying is that this light is now becoming much more suitable for iron. So it's changing the redox potential of that side, making it much harder to oxidate. And that pushes that iron 3, iron 2 potential to a position where it then starts to compete with the anion. However, after all this sort of effort, you find that you thought making lithium ion cathodes out of iron was hard, and you discover it's even harder than you thought it was. Because the irreversible iron redox is the real killer, unless you can find a way to switch that off. These iron-based cathode materials aren't really going to work. So just the main thing, technically we did the work, so the CRFX2 stuff I was talking about, the work with single graduate student Saraj, and then Debbie did the published stuff I was before. Very grateful for our colleagues at Warwick and the RIP station, Sweden Street and Sheffield was cycling for us. You can see we used a lot of external facilities. It's thinking from X-ray and X-ray absorption, diffraction, lots of neutron diffraction, and I think these are the Faraday's student DBTech project for funding. Thank you very much for your attention.